So today we have Jay Reynolson here. He's coming all the way from San Diego today. He's a former JPL employee and senior research fellow at Caltech from 1961 to 1974. He was an original co-investigator on the Surveyor television experiment and a member of the Lunar Geology Investigative Team on all of the Apollo landed missions. He was also involved in the analysis of the returned parts from Apollo 12. So everyone, please give a warm welcome to Jay Reynolson.
This month, we celebrated a special event. That was Apollo 12's landing on the moon 50 years before. It was special because they came and visited another spot, our Surveyor 3, that had landed 2.5 years earlier. Well, here is a picture of the Surveyor landing on Oceanus Pacificus. Here is a shot of the launch of one of our Surveyor. That was the first one.
Gas looks good. Doppler readout is nominal. Chamber pressure looks good. Liftoff was at 7:41 Pacific Daylight Time on an azimuth of 102 degrees.
Now, here's the separation between Centaur, was the second stage. You see the legs are expanded. Now it's on the way to the moon. At about 25,000 feet above the surface, the retrorocket would start, and it would slow the entire spacecraft from about 3,000 feet per second to about 350. And then at that time, they would also light 3 thrusters, and they would also slow everything down. And at one point, 13 feet above the surface, they're supposed to cut off, and they're supposed to gently fall at about 5 feet per second to the surface. Well, it didn't quite end that way. Here's the diagram of Surveyor 3 before landing. And in this particular case, the vernier thrusters had enough power that they compensated the entire weight of the spacecraft. So it just lifted off again, and then it landed, and then it lifted off again, and then landed. Finally, we said, oh, this is not working automatically. So we sent commands from Goldstone, and that cut off the thrusters. So we had now 3 footprints on the lunar surface, and you can see from the bottom the kind of gap in between each one of these stops. What happened? All right, we had a radar, altitude and Doppler sensor called a RADVIS, and that was to control everything. Now, there's a beam 4, you can probably see the beam form over here, and that was set along the velocity vector as we were coming down, also the same axis as the retrorocket, and we lost lock with Goldstone. So obviously, they didn't cut things off at 13 feet. And the other 3 are really determined the attitude of the entire spacecraft on its mission to the moon, including mid-course correction and so forth. Here is a picture of the Lunar Orbiter 3. Now remember, about 3 years ago, I gave a talk about Surveyor 1, and we landed there completely blind because we had no lunar orbiter pictures. Well, when 3 landed, we had the lunar orbiter. And so this is an example. There's a couple of craters, some rocks, things like that, which we're still going to be talking about. Ewan Whitaker, who is a member of our Surveyor television team, was really good in picking out where we had landed by resection. And he had done this. He was also a co-investigator on Ranger. Remember, that was the one where we came down in the moon, and we took a couple of pictures before we crashed in to get high resolution. So he actually zoomed in and found exactly where he had landed. That is an important event because we're going to talk about that a little later. Here is a topographic map of the sphere. Now, the ones in color that you see are some of the prominent features. This one, particularly here, if I can point that out, is two great big rocks. And those rocks you and use very much for coming back and finding the surveyor. Surveyor is this last red circle down at the bottom. Now, this is a high-resolution photograph taken by the Lunar Reconnaissance Orbiter camera, which we have today, and it's still going around the moon. And it's really great. I didn't want to do that one. So the surveyor lander, excuse me, the Apollo 12 is over on this side. And if I can point that out. And this is a block crater where I'm going to talk a little bit later on. And then here is the position of Surveyor 3. And this is the huge Surveyor crater, which we'll call about 200 meters in diameter. So the marks, if you can see the black marks, I don't know, they don't show up too well there. Those were the tracks of the astronauts as they went out on their 2 extravehicular activities, EVAs. And it's interesting because the resolution on this is in the order of centimeters. And we're still doing these images. It's just amazing today. Now, here is a photograph of Doctors Gene and Carolyn Shoemaker. And this is taken at Mount Palomar Observatory. And it was taken in, I believe that was the time they discovered the comet. That was in July 1994. If any of you remember that. Well, Gene was important because he was the principal investigator for the Surveyor television experiment. And he went on to become the chairman of what we call the Lunar Geology Exploration Team on all of Apollo 11 and 12. Later on, there were a team on every single one of those missions, and they were respectively geologists in the most part. So he was instrumental in our initial effort. I joined JPL in 1961, and when I joined, I was given a task called cognizant scientist. Now, what the cognizant scientist is supposed to do is act as liaison to the co-investigator, to the principal investigator with lab. They had a team. And so I had never met Gene, and I found out that he was with the United States Geological Survey, and at the time it was at Menlo Park in Northern California. So I made a phone call, and he said, "Oh, Jay, well, I'd like to meet you, but I won't be there. I'm going to be at the Meteor Crater in Arizona." And that's a great crater. You have to see that. And why don't you meet me there? So I did, and I flew into Flagstaff. Their Flagstaff is in the far distance with the snow-capped mountains. And I drove to Winslow, walked over to the edge of the crater, and there was Gene way down on the bottom. Now, he had gotten his PhD on that crater. So I waited, and he climbed up, and then we spent about 2.5 hours just talking about what he wanted to do on the moon, from the standpoint of using that television camera as an experiment. So that was my first opportunity. Well, here's another group of people. The one from the left is Maria Suchert, and she is the archivist at the Lunar Planetary Lab at the University of Arizona in Tucson. The one in the middle is Ewan Whitaker, and I mentioned him before. And I don't know who the other guy to the right, but anyway, he had kept all of the 70-millimeter film that we had taken and copied from our magnetic tapes, and he stored them all. Well, after a couple of years ago, we got a national grant to digitize all of the images that we had collected every place else. I keep jumping back and forth. And so it ended up, there must be a time limit on this, and I didn't know what it was, sorry. And so we've ended up digitizing. We have now 70 That's going to be 93,000 images, all stored on a 4 terabyte hard drive. So that was a very, very big step. Here is our television camera. The one to the right is actually a blow-up of the very upper part of that camera. And it depended upon a mirror that looked up and would rotate almost 360 degrees, and then it would move in elevation from 40 degrees above to 60 degrees below. And it had a filter wheel that you could rotate, had 4 positions that it had. Now, if you look at the left side, shows the breakdown. Right after the filter wheel, there was a zoom lens. And the zoom lens went from 100 millimeters to 25 millimeters. We only used it at each end to be safe. Below that was a shutter, and then there was a Vidicon. I have an example of the Vidicon in one of these tables over here you can take a look at. The shutter is very unique because it had a capability. So it had 2 blades, and it would open it and move like this, which gave us 150 milliseconds. Or they would open one blade and then close it, and we got 1.2 seconds. But we had a third one. And the third one is we would open up both blades. And then we would go in and turn off the electron scanning beam inside the Vidicon. And now we could integrate all of the photons from 5 minutes to 30 minutes. So we created basically what I would like to call the first astronomical telescope on the lunar surface. Because we were taking the same thing you do if you have an observatory, and you open the telescope, move your plate, set your film in there, and you allow it to expose for a certain period of time. When you're done, you close the shutter and you process your plate. We're doing the same thing on the moon. So that really is something. Now, it's not very big, so it's like Galileo's telescope. Nevertheless, it was the very first. Here is a color image showing the footpad. That was one of the footpads of the leg 2 on the Surveyor spacecraft. And right above it, I should say right there, a little bit below it, if I can move that back here, is a photometric target. And there's 2 photometric targets on the table that you can take a look at. Those we use for photometric calibration and recheck of our pre-flight calibration. And we use that. Above it, a little bit, I don't know whether you can see that, is a gold tip. That was one of the thrusters that we had on the lake. And then there was a bunch of lunar soil. And that lunar soil was put on this instrument right beside it in blue. It's an extended arm with a scoop. And we call that extended arm as soil mechanics. That is, how hard is the surface of the moon. And the other one was a scoop, the surface sampler, which came and put the soil on top of the footpad. Now, why did we have to do this? Remember, 4 months before Surveyor 1 landed, the Soviets landed a capsule on the moon. And it was pretty light, and it didn't sink in like somebody said we would. And then we landed our Surveyor, which was a good deal heavier than that capsule. And then they were going to land the LIM, which is even heavier. So we still didn't have complete faith in that the fact that the lunar surface would support all of us. So we needed to measure that. And that was this instrument, the SMSS, actually ended up doing. Here is a sketch of all the spots that the SMSS did. And the circle is really one showing that this is a trench that they dug. Alan Bean, who was the second astronaut on the moon, Pete Conrad was the first, and Alan Bean took pictures of this, and I'll show you a little bit later on. This is a first solar eclipse that we saw from the moon, taken by Surveyor 3. We took 2 exposures, or on the far left, about 30 minutes apart, and then we combined all those 3 black and white images through 3 colors into 2 types. One was done way back, shortly after mission. The other one was done by Park Squires, my optics tech. And he did it, and it's a little bit better resolution. The beads that we saw were traced by cloud-free areas on the atmosphere that surrounds the Earth. And we found that out by using ESA photographs, which were satellites at that time, and would map all of the clouds. So you could go ahead and find out exactly which were cloud-free and which were covered. So those were spots that we found. Well, what did the astronauts do on their way back from about 30,000 away from landing? They took a solar eclipse as well. And if you look very carefully at the very, very top up here, there's a couple of little spots. These are, again, cloud-free areas that they picked up. They were pretty close, but it's a spectacular area. So here was astronaut from 12 looking at stuff we had taken 2.5 years earlier. Well, another thing we took, very first color image of the crescent Earth taken from the moon. And so that was, again, unfortunately, we had to use a wide angle for that, so it was 25 millimeter focal length. So it's only about 44 pixels square. Well, here is on the right, or excuse me, on the left, a picture of Mars. Mariner 9 was about to go into orbit around Mars, and they were going to take a whole bunch of color pictures. This is the kind of filter wheel that we're using. We used that also on Mars. Unfortunately, the filter wheel stopped, and therefore we had a problem. This is the color reconstitution apparatus which we used at that time. And we used basically 3 color sources. There were xenon arc, so that you had the spectrum very close to that of the sunlight on the moon. We used black and white images, and these were calibrated by our pre-flight calibration, looking at specific colors. We then would combine all of these to get an image that we could look at with a pair of binocular eyepieces. And we got those all in register, so we had our color reproduction. The iris in each one of these were adjusted and calibrated spectroradiometrically, so we had direct calibration of this entire instrument. When we reproduced the color, we also photographed it on 35 millimeter film. And what we would do, we would take and put that in the 4th white source down here, and we'd have a mirror that would rotate back and forth. And when we ended up doing that, we could do a comparison. Might be a not exactly good comparison, so you'd ask some color compensation filters. When you got done, you had a good 35 millimeter slide. Now you pass that out to the press, and you say, okay, this is the best color that we have really obtained. Now, if you're printing that out, and you're putting on that publishing, use that 35 millimeter as your color control. All right, what we ended up doing, this is a combination using the International System of Color, called a CIE system. And it required fitting filters to our Vidicon spectral responsivity. So we would match as close as possible to this requirement for international color. And what we used is Dr. Gutevishetsky as our color consultant. He is the author of Color Science. So for the first time, we had taken not only a a television camera, created it to an astronomical instrument, but we also created the first colorimeter on the lunar surface. So the colors that we're measuring are the most accurate color ever since that time. Here's an example of all the points that we have on the left, showing the various parts of the solar eclipse and also the part of the Earth. And then on the right is simply the colors. The peripheral, that is the entire area, are all colors that could be generated. The locus that you have on that is actually the black body locus measured in degrees Kelvin. And it shows you pretty much how those colors were derived. Now let's talk about Apollo 12. They had 3 basic requirements. They said they wanted to go someplace on the lunar surface that they knew exactly where it was, and they would be able to land and be within 100 meters of where they wanted. And this was very desirable because remember Apollo 11 this year as well, and Neil Armstrong was sitting there. We told him where we wanted him to go, and when he got close, he said, "Well, I don't want to land there." And so he continued to go about 4 miles. Well, we didn't want to do this on every single Apollo mission. So we wanted to go exactly where we knew something was. What better? Surveyor 3. Ewan Whitaker said, "Now I know exactly where it is." So Pete took control, and they started from the east. That's the one to the right. And they came over close to where this surveyor actually had landed. Actually, they came in pretty close. They came 109 meters away, which is about 357 feet. And they were supposed to be, by his rules, be more than 500 away. Well, okay, so we got a little close. And he thought, well, I was still pretty good. But he forgot that with all of the retro rocket that he used, he was blowing lots of dust all over, and there's no atmosphere. So those dust particles, they go for hundreds of meters. And it probably covered, and it did cover Surveyor 3 to a degree. So this sort of gives you an example of his approach to the lunar crater. Here is a United States Geological Survey map. In red, it shows the area of the EVAs that both Pete Conrad and Alan Bean took. The blues are the areas where we felt it was important for them to take samples and bring them back. And then the yellow was an arrow point where the whatever astronaut it was, Pete or Al, would take pictures of that sample, and they had the orientation. All the other numbers are simply the film identification. So you go back into the website, which have been nicely categorized on all the images from Apollo 12, and you can pick out one of those numbers, and it'll show you what that picture looked like. All right, here is the Surveyor crater, and you can see Surveyor 3 sitting there. There is an area right here, way over top, is called the Block Crater, right at the horizon at the very top. It's an interesting crater, and it's Block Crater because there's a lot of blocks of rocks around it. I'll talk about it a little later. And way over on the far left up there is the LIM, the Lunar Excursion Module that Pete Conrad and Alan B. came in. There's a whole bunch of other things that Alan took pictures of. He thought it was very impressive. There were fractures. They saw linear fissions. And those were probably due to the cracking of the surface when the impact of the Surveyor crater occurred many, many, many years ago. Now, here's a blow-up of that Block Crater, and we were blowing it up. Now, I looked at this and preparing, and I said, gee, there's an interesting rock. See that pyramid rock that's circled in red? Now, look at that very carefully because it's a pyramid rock like this. And yet the light reflected from that fairly flat surface is following the same shape as that pyramid. I said, gee, that's interesting. That's got to be a pretty specular or reflective surface. I wonder what it's made out of. Here is a photograph that my son had done, a panorama, I should say. Now, one of the problems we had when we landed on Surveyor is that the dust that was kicked up by our 3 landings coated the upper part of the mirror. And so you've got a lot of cloudy stuff that you're looking through, and you can see stuff in that, but you have to pull it out. And then there'd be other parts of that same image that were clear of the dust and very sharp. So each one of these with a mirror moving around had you put together. Each one had to be individually corrected. And then you put them together and at a nice pan, eliminate all the edges. So he did a pretty good job, not perfect. And there's a couple of big rocks right in the middle there. Those are the ones that Ewan, again, used to identify where Surveyor 3 had landed. So it's an example. And I think I had also that rock in red. Does that say up there? And that little red at the top. Is that in red? Okay. This is what one image looks like. And you can see it's pretty clear down at the bottom. But the upper top, all covered with dust, has to be extracted. There is a crater you can probably just faintly see on that. I don't know whether that contrast on the screen is that good, but it's about an idea. All right, now, how do we do this? Well, we had a surveyor. This is the top sketch in blue. And the center point of all that circle was the optical axis of the camera. We divided 360 degrees, or almost a circle, into 19 parts. You have to put all those together. You make sure that everything is oriented, selenographic, so you know which way is north, and that creates your panorama. A lot of digital work. All right, here is another topo, and there's also a cross section, that straight line all the way across. And if you go down below, you can see where the surveyor landed on that basis. Next to it is a book, and it's also on this table. And that book is an analysis of everything they did when they brought the parts back. Pretty extensive, and I'll get a little bit more into that as we go on. All right, here's one of the problems that the astronauts have on the lunar surface, and they had actually two major ones for monitoring around. One is to estimate distances. And on the Earth, we don't have too much of a problem because we can look at it. It's pretty hazy. Maybe it's somewhat bluish, and we say that's pretty far away. But there is no atmosphere on the moon, so you're actually judging distances which are really hard to do. Here is the block crater about 85 meters away from the surveyor. There's another one, those two big rocks that are about, I think that says 60. And then there's another crater about 25. And then way down there, of course, you have your surveyor you're looking at. Here is the lunar orbiter stuff, the reconnaissance orbiter, showing those distances. And every one of them is about equally distant. And then when you look at that area on the right, it's very confusing. Another thing they had was that when the sunlight was directly behind them, they had an effect called a retroreflection, or the returned light in the direction. And that would wipe out all the contrasts that you had. And if you were walking on the lunar surface and you lost that and you're looking straight down sun, it could be a rock there, it could be a crater, you could fall in, and you don't want to do that. And so consequently, one of the tricks the astronauts had was constantly looking this way, not directly down sun, so they wouldn't be in danger. All right, here's a Hasselblad camera mounted on Alan Bean's suit. And I'll talk a little bit about the Hasselblad because that has a direct relevance. Hasselblad is a camera that was built in Sweden, and the entire enclosure was shipped to Carl Zeiss in Oberkochen, Germany. And when they would get it, they would put a 60 millimeter lens that they use for all the data cameras. There were just 2 data cameras on the moon for the astronauts. And they would then do some initial tests, things like that was essential. And they would package it up and send it off to Houston. Well, the Lunar Geological Exploration Team, and particularly Henry Holt, who was my colleague and also a geologist, we were required by the chairman of that team to calibrate those cameras pre-flight. So we ended up doing that either at the Cape or at the Manned Spacecraft Center. Here's one of our setups that we did. And here's an example. This is without the magazine. We set up the camera. We had a suspended light source, which the camera was looking at. had a fiber optics bundle which would automatically move the entire area of the camera. Now, the camera had, for the data cameras, a glass platen just before the film. And inscribed on that glass platen was a series of crosses. And that was used to estimate sizes of things we were looking at and also correct any distortion you might have. So we did that. Now, the people involved, this is Henry Holt on the far right. The one in the middle is Carolyn Shoemaker, and the one on the left is my wife, Renata. This is an example of what we've done. This is what we call a camera shading, and each one of those contours would tell us how far we had to make a correction when we were extracting photometric information from the film itself. We did a calibration like this on a whole bunch of various f-stops and a bunch of other things. We had to measure shutter. We had to measure iris repeatability. We had to measure the response function, the R&D functions you have from film. We had to measure the modulation transfer function, the resolution of that particular camera, and we had to measure the veiling glare. Well, here is another little story. These are three people that I was very close to. These were colleagues when I did my graduate studies in Berlin at the Technical University and the Optical Institute. The one on the far left is Gunther Kirchhoff, who went on to be at the head of the design department at Agfa Camera Company, a competitor to Eastman Kodak. One in the middle is my wife, and on the far right is Joachim Kammerer. And Joachim Kammerer, when he finished, he went to Carl Zeiss in Oberkochen. He built himself up and eventually became the head of the optics department at Zeiss. And we were over there one year visiting. You knew all the family and the kids and everything else. And he says, Jay, would you like to come up to my office? I just retired a year ago and see where I did all my work. Yeah, great. So we went to his office, and on the wall way up here was all those beautiful pictures of Apollo, all the different missions that he had been sent by his people. And then he started talking about the work he had to do with the Hasselblad data camera. And he kept getting all these little notices. Take a look in the veiling glare in that particular camera. That was from Houston, the Manned Spacecraft Center. And it kept going back and forth. He said it was really frustrating. And as he was talking, I started smiling, or grinning a little bit. He says, Jay, what's so funny? Why are you smiling? He said, you want to know who wrote all those things to do? We did. And we burst out of laughter. I said, had we known that, we could have picked up the phone call and said, hey, Joachim, how's everything going? How's the family? Hey, we've got some measurements we're taking on the camera, and we found there's a lot of extra light not coming from what we're examining. Sort of a little bit of veiling glare. Probably need a little black thing inside the housing, maybe even one or two baffles. He said, okay, yeah, but don't tell Houston. Now, another little problem Al Beam had, and it has quite a bit, was the camera. Alan was out there on EVA-2, and all of a sudden he noticed that the whole bracket fell away and the whole camera was lost on the lunar surface. He did keep the magazine. What happened? Here's a diagram of that apparatus. Here is the electric control right here. So when you click that, it automatically advances electrically the film. And here's the arm, and here's this little piece sticking out. The astronauts would grab that with their hand, squeeze it, and it would automatically trigger the advance. Now, holding this whole thing is a set screw on a thumb screw. When you tighten something on a tripod, you got a thumb screw and you tighten it on, that tightens the whole thing. And here's a set screw. They're moving around. the set screw gets loose. You know how big a wrench is on a set screw? With a great big glove, you're not going to do it. You got to get back in the limb and take it apart, change it all. Well, what happened? It fell, so the whole piece dropped to the surface. So, boy, that was a loss. So for rear or in, he had to use Pete Conrad's camera to do all of the pictures, which is what he did. All right, now they did this for 12. And then he said, boy, that was not very good. So we're going to have a straight pin. And now they supposedly, for all the rest of the missions, they didn't have that problem. Well, unfortunately, Al had another problem because if you remember correctly, there was supposed to be a 60-millimeter camera that was put on the surface after they got out of the limb. Now, they did this in Apollo 11, but it was a black and white camera. So for 12, they had one with color, and that was to be commanded from the Earth. So there was something on his sleeve. There was no lens cap, incidentally, on that said, be very careful that you don't point the camera at the sun or big reflective stuff from the limb. And he didn't, and the sun hit it and eliminated that entire image. Poor Al. Anyway, so here is another shot of a surveyor sitting in the crater, and that had a tilt of about 12.5 degrees. But the camera itself was actually tilted with respect to the spacecraft. It's another story. And it wasn't oriented along the pole or the main mast that supported the planar array and the solar antenna. So we had a combination of 12.5 and 16, almost 30 degrees, and we're in the equatorial area of the moon, which meant we could see the home planet. So we got our solar eclipse, we got our color stuff from the Earth because we just fortuitously landed at the right attitude. The gods were with us. Here's another shot, and this shows the surveyor. There's land 2, leg 2, and leg 1. That's the one over here. And also in the far foreground, right up at the horizon is the block crater. All right, when they landed, Surveyor 2's leg made 2 footprints right on the lunar surface. And if you look very carefully at that one, you can see sort of a pattern that exists. Well, in actuality, this is what the footpad looked like. It was hexagonal aluminum put together, covered with aluminum. And at the very top of it, you have a hexagonal pattern. And that pattern was reflected in that spot. Well, Al was response. He has the camera. He's supposed to take pictures of the entire spacecraft and the whole bit. And he did. And he went around and he took pictures. And what happened to the footprint? So poor Al, he had not had archaeology references 1A. And that is, you get away and you don't touch anything before you've taken all the pictures. So Edison's, all of the spacecraft's footprints are gone, but Alan Bean's is still there. Here's another shot, and it's a close-up of the camera. Here's one of Pete. Alan took that picture of. Pete took the picture. They switched cameras, and that was the picture of Alan. And here is a picture, again, of the camera itself, and it's all white. You don't see a lot of stuff from the camera. So Pete reached over and he said, I wonder if the dust comes off. So he took his finger and he swiped it. And sure enough, the dust came off. Not all of it, but some of it. And so anyway, here is, if you take this film and you blow it up, you can actually still see reflection from that particular mirror. There's the swipe, and you can see the rest of the shape of the housing. And there's a little spot down there, which is actually the tip of the motor that moved the filter wheel. Okay, here's Alan's photo. Now, there is a story that people probably remember. Alan Beam snuck off before flight time to get a timer from one of the stores. And what was he going to do with the timer? Well, he thought he'd take a timer. Remember that pole that I showed you? You can take that off. They had a special sampler which went down into the ground, so they didn't need a tripod. The whole thing fit on top of it, so they would have something standing here. There would be the timer. There would be the camera would be mounted up because we didn't take it. I mean, the camera was attached to the bracket, and he would then move down beside Pete, and they would take a picture of both of them standing there. And they said this would really, really irk those people that said we never went to the moon. It was all done in the studio. And they say, see, there's the proof. There were two standing side by side. Who took the picture? That was done in the studio. Well, if you remember correctly, maybe you don't, Life magazine turned out a front cover with both of them standing side by side. That was all done photographically. Anyway, they couldn't find the timer. So thank goodness it didn't happen. Here's one of the other areas. That's leg 1, and it dug into the surface a little bit. You can see that. Then we had a compartment A, and Alan said, well, let's go over and see if there's any dust on the top of that. And he went and looked at it, and they said, oh, yeah, there was a little bit. They tried to get the mirror away, but in accidents, that compartment was somewhat sheltered, so that the dust that was thrown up from our landing was really blocked by a lot of that compartment. So most of the stuff that we see there was due to Apollo 12. All right, here is one of the trenches that the SMSS dug, and the arrow points in the direction in which Alan was supposed to take a picture. There's the trenches, and the scoop they cut off. They cut off a bunch of other cables and other tubes, and the camera, and brought them all back to Earth. Here's what the spacecraft looks like now with those parts gone. If you go back, you can see everything remaining pristine for maybe eons of time. Now, here is a shot of that particular pointed rock I mentioned. This is taken from Block Crater. Alan took this looking down into the crater. You can see the spacecraft up there, and it's encircled. And there is the pointed rock. And so here is a blow up of that. That's in the right side, and you can see that face of that rock is very flat. And if you look at it, that is a sample which we think that Pete brought back, and it had black glass on it. So it was really reflecting a large part of that light and giving that particular pattern. That's very nice. Here's a shot of a gnomon. This is a piece that we have to put in order to take pictures. Remember, there isn't any horizon on the lunar surface. So what you do, you have this rod that has a gimbal mount, goes straight up. That's the zenith. 90 degrees from that gives you your horizon. So this is Pete's shadow. Over there's the gnomon. You had to place that down before you took pictures. You took pictures, the gnomon, before you picked the sample up. Then you picked the sample up, took another picture of that. And not only one picture, they would be in this orientation. We told them what f-stop to use and how to take these pictures. That's what Henry Holt and I had to do. And here is that rock flipped over a little bit. And anyway, it has an actual number as well, so you can hunt for it. Oh, we brought the camera back. And when we first got it in to Houston, you could see the mark on the mirror. And it was sort of a brown tan. Some of it could be the lunar dust, but some of it was the photo bleaching that we did for the white paint that the camera was painted with. All right, here are some micro photographs that we took. We found that there's a lot of glass spheres, and glass is really a very significant part of that lunar sample. And then on the right, this is the hunk of what they call pyrocene grain. The long fiber is actually an artifact coming from the beta cloth fiber that was used when they stowed the camera. Now, I've my feeling is that a good deal of the retroreflection or the photometric function of the lunar surface is due to a large degree by the amount of glass that we found in the soil. The astronauts kept talking about the glass almost on every single Apollo mission. And when we look at a full moon, as a very, very sharp peak, it's very, very bright. So we say the phase angle, which is the angle at which the sunlight hits the surface and the direction in which it comes back. And when that becomes zero, it's the maximum peak. This was an in situ measurement we did on Surveyor 1. So it gives you an example. And if you look at the areas in which they're proposed, they're very similar. Actually, one of the correlations you can use in a day-to-day work, there are glass beads in your pavement marking as you're driving along. And the area of your pavement marking is about 30% of that entire area of the paint. And that's equivalent about the same kind of glass that you would have in the soil. We did photometric measurements, polarimetric measurements on the mirror with a special apparatus that was done at Flagstaff. And then we also used a goniospectral polarimeter. So we actually measure at all different angles the spectral properties of the lunar dust on that particular mirror. Very, very extensive mirror situation, and that's all written up here in that particular book, which is incidentally you can get on the internet, all of the stuff. Now, one of the things we had problems is if you look at small areas, you got to take a lot of areas to look at. But if you use what we call white light polarimetry, then everything that is blocked with the analyzer where it's crossed leaves all the rest of that to generate the color. So everything external to that would give you a resultant color. And colors that have areas of that mirror would have the same color, would be the same level of any deposit that we had. There was a question. The mirror is made out of beryllium, hence an overcoat of metal, of nickel. And nickel can be polished just like the surface of an optical glass. And then on top of that, you had an overcoat of aluminum for reflection and a silicon monoxide coating on the top of that to protect that aluminum. And then maybe there was another coating someplace in between, and there were lunar files. The thought was that in transit for the surveyor, they turned on the thrusters for a mid-course correction, and that threw material up on the mirror itself. So we did analysis using this white type polarimetry. Filter wheel had a lot of stuff on it. The clear that had was the closest to the front part of the camera had the most. And the numbers that are listed on here are the percentages of the fines, that is the material you would have compared to the overall area. We also found that the filters actually had more transmittance than we had before they left. Some of that may have been because some of these filter wheel has actually have two layers. We put an Inconel coating on one of those filters because what we wanted to do is when we moved through 3 filters, we didn't want to change the F number because that was an uncertainty added on to our uncertainty of a regular measurement. So we kept that all, and it could very well be that the Inconel had an effect over the 2.5 years and licensed. Maybe it wasn't as dense, and therefore the transmission was higher. Well, one last thing is a little bit of PR. David Criswell and I, when I was at the campus, said that the lunar particles have a unique property, especially when the terminator, that line between day and night, exists. And they can have various charges, positive charge, negative charge, things like that. So we proposed, here's a horizon from Apollo 7. It's about 150 meters away, so it's fairly close. The contour follows the same thing as the upper rocks that we had on the surface. And so our hypothesis is that there was an electrostatic field that actually levitated lunar dust. And the sunlight below the horizon after sunset would illuminate that dust like a sun behind a cloud. And so we have a time lapse picture of that. Look at it very carefully now. Watch. It's dimming and it's also moving. We're at 40 degrees southern latitude. So the sun line is going down at this angle. Well, anyway, this is our philosophy. And that's 52 years ago. And I've yet to see anybody take another picture of it. So I hope before I go, somebody will to either confirm it or reject it. And Jack Schmidt is a good friend of mine, the astronaut on Apollo 17. And I saw him recently this year. And I asked him about our philosophy, and he said, well, I know, Jay, I don't agree with it. Why don't you agree with it? Well, I said, I looked at all the rocks, and all rocks look clean. So I don't understand it. So I said, okay, Jack, you're a geologist. Explain it. Huh, I can't. So we'll have to wait till somebody else comes, all right? I don't know that you can read all this, but we did all kinds of wonderful things afterward. We looked at, there was about 40 individual teams with 6 different countries that analyzed all of these parts that they took off. And it shows all these other things. We looked at the mirror. We looked at something on the Vidicon. The shutter had been open. It was exposed. Maybe there was reverberation of the photoconductive surface, etc. And then there was a recommendation to the end of that. They said, and any time you're putting anything out in space, put on a coupon. That's not something you get money for. It is something, it's a characteristic of some material you have. You want to find out what the environment's going to do to that, put it down someplace on your spacecraft and go ahead and monitor it, or anybody coming back to the eons of time will look at it and do an evaluation. It's like looking and uncovering things in the pyramids, etc. And so this is a very extensive review that we did. So I want to thank you all for coming to JPL's Sacred Place. Okay? Live well and prosper.
All right. So if anyone has any questions at this time, we can do that. Just raise your hand. Here, let me bring the mic to you.
Yep.
Yes, can you comment on if you've thought through what is the mechanism for the dust depositing on the mirror? Because conventional wisdom is that landing in a vacuum, all the dust kind of goes out ballistically, and
Yeah.
unless you have secondary bounces, it won't come back and contaminate the spacecraft. So that's kind of puzzling why that happened.
Yeah. Now, the question was what's happened in not only the particles, the particles going out, but there is a reflex work that comes back. Is that correct? I don't know whether we really studied that. I think the idea was the fact that there could have been additional contribution from particles that would, say, hit the mirror and then would bounce someplace else in the spacecraft. Is that what you had in mind?
I was thinking about it. Now, things getting on the mirror. We're designing the lunar landers now, and we're trying to save mass. We've said maybe we don't need covers on our sensitive optics because the chances of a secondary reflection of a dust particle coming back and hitting your optics is very small.
Yeah.
But it sounds like if you're seeing dust in your imagery taken with your surveyor, that assumption is incorrect.
Yeah. Well, I don't have an answer for that. Anytime we obviously know right now with all the studies that the dust, lunar dust, is a real problem, and it's going to be continuing a problem when we go back to the moon. And we don't understand everything about the environment that's controlling that. and what other effects it has. It's a shame that after all these years, no one has gone back with it. That's just simple aspect of taking a high resolution image of what exactly is happening. Time lapse, just like what we did. But we did this 42 years ago. You think, what's happened? I mean, I can take my iPhone and I can put it in a little cavity which would have all the temperature constraints, everything else protected, and I would get a fantastic picture. Thousands, 10,000 times better than what I did on Surveyor. No one's done that. So eventually, somebody is going to do this. Somebody is going to open a whole new area. One of the thoughts that we had in discussing that, both Dave Criswell and myself, is that you remember there's a time interval that we measured. We measured this for an hour and a half after that phenomenon. Well, the moon's rotating, and it's rotating in an hour and a half. What happens to those particles? Do they go back down where they came from, or do they move? If they're coming back, you have an erosion process, something that's happening to the upper layer, very thin layer of the regolith, but it's still thin. And these are questions we still haven't answered. So I can't answer your question.
Maybe a secondary question then. So when you took those images and you saw the dust, evidence of dust on the mirror,
Yeah.
did it get worse throughout your surface mission, or do you think it was all deposited on landing?
No. The first question we had is we looked at the pictures that we had, and the upper part of the mirror was coated. But when we looked at everything else, the Apollo 12 had contributed a good deal more. They were close. They were 109 meters away. And even though they were 70, 67 meters up above, the tremendous force of their retro rocket before they landed was throwing these particles hundreds of meters away. And we found out that in many cases that there was an additional coating. For instance, that the top of compartment A, which was shielded from our first layer landing when we landed, that would have been clean. That should have been clean, and it wasn't. So there's a good indication that it was. Well, yes.
Hold on one sec. I'll bring the mic over.
You noted glass spheres on the mirror, I believe, right?
Yes.
Among the dust particles, there were glass spheres. Is it your thinking that those resulted from the Apollo landing or from some other just natural lunar regolith?
No, I think we're pretty sure that it occurred from the Apollo landing. That was a conclusion we came. And yeah, there was a lot of work on some of the structure. Len Jaffe, who was actually the chief scientist on Surveyor for a long time, he did a lot of work on this honeycomb pattern of that one footprint that he had. He went to find a whole bunch of things. And he was very convinced that a large part of that had been added by Apollo 12's landing. Now, Pete, when he landed, and we saw him afterward up in the Manned Spacecraft Center, and he's a very interesting, charismatic guy, very laid back. And he came jockeying on. He says, "Hey, what do you think about the rocks I brought for you?" And of course, he eventually got killed in a motorcycle accident. He was the kind of gung-ho. They were all Navy gung-ho fighters. And I think he said, I was very careful. I didn't want to contribute anything to the spacecraft. But you're dealing with something completely unknown, and there's lunar dust. And that's what happened. So I think from the analysis that we did, together with all the results of the people of the 40 teams at 6 countries, that they're pretty convinced. The one thing I do want to, however, emphasize, and people haven't asked me yet, there were supposedly microbes that they said in one of the tubes. And they said, oh, maybe these are the microbes that we had before we launched at the Cape, and they survived 2.5 years. Oh, there's a later study that said no, it was contamination, because we had not refined how well we protect something when we bring it back from space. And we got to be careful of that, because we're going to bring back samples from Mars. We're going to do a whole bunch of stuff. So the entire work that we take, we've got to be very careful of.
Any other questions?
Um, oh,
How did they get all the stuff off of the spacecraft? Did they have big cutters to cut the camera? How
yeah, they had
that?
great big huge cutters like the kind you buy at Home Depot, pretty sharp, and they were able to cut those except for one rod. Had one rod, and they were very careful because the rods were made and there was usually about that much of the rod that was really solid. And they said, well, you stay away from that so you can cut that. They tried to cut the tape from the scoop that was coming down on the SMFS, and that didn't work. It didn't work. And they kept working on it, and all of a sudden it just split. And that was where we had welded a couple parts, made a loop of that tape we had welded, and it just came apart. They didn't have to cut it. Otherwise, they would have had a problem. But no, the cutters were pretty sharp, and they did a pretty clean job on cutting everything. And they had the tubes they brought back. Some were painted, some were not painted, some were specular. So they did a quite analysis. And this, like I said, all of that document and what has been written, these are two JPLers that organized it, that were in charge of the entire organization of they had to use in order to get all those parts. And that's available on the internet. So you can go back and examine every single part. It was really thorough. I mean, they did particle analysis. They did stuff with the best equipment we had whatsoever, and everything anybody could think of.
Cool. Thank
Yeah.
Later on in time, digital detectors were invented and used for planetary imaging, like CCDs, CMOS, and all that. At the time you were doing all of your radiometry and photogrammetry and all that, were you aware of this new generation of detector coming along, or was that still an unforeseen thing?
I got the impression that it was sort of an unseen thing. I mean, there were ideas we were going to come, but this was the state of the art. It was used in television cameras, all the NBC, CBS. They all used that detector. Now, the difference between that detector and the one we had was we had to take 3.2 seconds for us to read out one frame, as opposed to 30 seconds I mean, 30 frames per second. And so consequently, we call that a slow scan Vidicon. And the reason for that was simply bandwidth. And then we had to cut that down. I think something we had in the distance. There were some people that talk at JPL. Don Montgomery, unfortunately, can't be here. He was the one that was instrumental on that analysis, and also during the surveyor generation, an expert on that particular Vidicon. It was a state of the art problem because the photoconductors, we wanted a certain spectral responsivity, and it came from General Electrodynamics Corporation just outside of Dallas. And they would put the photoconductor on with evaporation. We would measure the spectral responsivity, and we'd come up with one and say, oh, boy, that's ideal. It's perfect. That has more red because it was heavily generated toward the blue, and that would be ideal. They would try to make another copy, couldn't. So it was like, the ancient magicians. I'll mix it all together, and then we'll see what happens. And that's what happened. I think people had on the horizon other detectors, and of course, the real breakthrough was silicon.
I think we have time for one last question, so I'll give it to Julie.
Not actually a question, but a comment. First of all, the report that Jay's been referring to, the Surveyor 3 Apollo 12 report, it's available on the NASA Technical Reports server, and we have a hard copy that Jay has donated to the archives if you'd like to see any of the images. Some of the photos in the PDF file that's online are not as clear as they could be, so the hard copy will be here if you need to refer to it. And the question about how they removed the pieces. We have a slideshow going across the room if you're interested in seeing some photos of the astronauts who visited JPL. And they had kind of a funny moment when they were trying to use tin snips on the pieces, because of course we had a test lander, um, and they knew it wasn't going to work. They needed something bigger to cut the pieces off with. So, yeah, it's kind of interesting how that happened.
Okay. All right. Okay, well, why don't we give him one more round of applause for cover? Any